So we're So we're coming towards the end of the material, but somewhat coming to a bit of a crescendo, I think. And it is my favorite bit of the course. And we are getting towards, we're gonna. The proof of the law of quadratic reciprocity itself is quite good, quite an achievement for us to get to in this class, and it's got some very interesting consequences in the final set of tutorial exercises. Some nice, interesting results we're going to be able to prove. So, like literally a quick 1 minute just review to bring us back up to speed. We've got our Legendre symbol, +1, -1, +1 when n is a quadratic residue, mod p, i.e. n equals n congruent to u squared, some u. N is not such a thing. Okay, so that's our Legendre symbol. It's our indicator function. 0 if n p divides n. Well, we don't really encounter the 0 case. We're mostly dealing with things that are numbers that are co-prime to p. So +1 if it's a quadratic residue, -1 if it's not. And our first kind of major insight into this was Euler's criterion, where we proved that NP was always congruent to n to the power of p minus 1 over 2 modulo p. Okay, so we proved that a few lectures ago. Previous to that, we'd just been working with the definition of the Legendre symbol and quadratic residue, and we're just been finding out whether things were or not quadratic residues just by brute force calculation, just squaring everything and looking at which things arose as squares and which things did. Euler's criterion was our first kind of bit of an insight into how being a quadratic residue or not depends on the number n. Okay. So it's to do with what this power of n is going to be congruent to ±2, because when you square it, remember when you square it, you get n to the power of p minus 1, which by Fermat's little theorem tells you is congruent to 1. So this thing, which is the square root of 1, has to be ±1. And in the proof of it, we were just checking that it agrees with this value being ±1. Applications of this, we saw that the -1 mod p was a quadratic residue exactly when p was congruent to 1 mod 4, and a non-residue when p is congruent to 3 mod 4, and the status of 2p. This was +1 and -1 according to the status of p modulo 8. And if I remember correctly, it was +1 when p is congruent to ±1, and -1 when p was congruent to ±3 on that. So these were applications of Euler's criterion. And that kind of brings us up to where we find ourselves now. Oh yeah, just to remind you of the law of quadratic reciprocity, which in the last lecture we did a kind of I tried to reenact the discovery of the law of quadratic reciprocity. How you might discover this law by investigating the residue status of one prime modulo another. So here you've got p and q, both odd primes. Distinct odd primes, say. And what the law of quadratic reciprocity tells you is it doesn't tell you exactly whether p is a quadratic residue mod q or not, but it relates the status of p mod q to q mod p. And remember, these are Legendre symbols, so they're either plus or minus 1. So either the two Legendre symbols are equal, or one is the negative of the other. Now, from the naive starting point, just from the definition of quadratic residues and that, there's nothing really signaling that there should be any particular there's nothing signaling strongly, I don't think, that there should be any particular connection between these two. Okay? The residue status of one prime modulo another. What we saw in the calculations and with the plots we were doing of comparing the plus and minus ones and whether the plot of P mod Q, whether it was symmetric or not, we discovered the law, or we discovered on the primes between 0 and 200, we saw some regular systematic behavior and conjectured that this applied always. Oh, I should have put these the other way around. Yeah, so they're the negative of each other when they're both congruent to 3 mod 4. Now that looks a bit odd because we've got the otherwise case first, but the otherwise applies to not this. Yeah. So if both of them are congruent to 3 mod 4, then their Legendre symbols are the opposite status. So one is a quadratic residue modulo the other one, and the other one isn't. It's not saying which one is the residue and which one isn't. It's just saying they have the opposite status. Whereas if this is not true, if at least one of the primes is congruent to 1 mod 4, remember all odd primes are 1 or 3 mod 4. If at least one of them is congruent to 1 mod 4, then the two Legendre symbols are equal. So they're either both residues mod each other, or they're both non-residues mod each other. And this enabled an algorithm to compute any NP. This is going on for longer in a minute, but anyway. To compute NP using the prime factorization of N. Okay? Which we investigated our first example of yesterday, and we're going to do some work with that in the tutorial and in the tutorials tomorrow. That was factorize, flip, reduce algorithm. Not its official name or anything. Okay, so we'll look at that in the tutorials tomorrow. Okay. Right. So this is quite an important result. It enables this algorithm, and it gives lots and lots of other insights. So lots of further number theory built, makes progress with the benefit of this law of quadratic reciprocity. Okay. But we haven't proved it. We discovered it by looking at a load of examples of primes, and we discovered that this was going on. But of course, there's an infinite number of prime numbers, so no amount of tinkering around with examples will ever fully establish this. We need a rigorous argument. Okay? So that's what we're starting to work towards now. Okay. So our first result, and we build it up in stages. So the first result is theorem 4.7, which is attributed to Gauss. Sometimes might be called Gauss's lemma. Gauss's formula or something. Anyway, it doesn't have a particularly fixed name, I don't think. Now this generalizes the idea from these applications. By these applications, I mean these guys here. Okay? Those two applications of Euler's criterion, where we settled the status of -1 mod P, we settled the status of 2 mod P based on P mod 4 and 8. If you take the idea from that, we can generalize it, and we get the Gauss's lemma. I'm wondering whether to work through this on the paper or go for it. Just read it off the notes. Let me see. You know what? I think it's pretty well spelled out in the notes, as is most of the proof type arguments. And I'd like to get through it in the next theorem. So to save on all the writing down, I don't think I'm going to contribute much more to it in writing it on the page than what I've got in the notes. Okay. So if you don't mind, we'll go to the notes to talk through this. First of all, any questions on the review or anything you're unsure about that needs clarification? Okay, so here's the generalization. Now remember, the key idea from the earlier applications was multiplying together a load of a kind of complete set of the residues and factorizing it in various ways. Identifying the presence of a factorial in both expressions, which we could cancel, and then we saw something interesting. And that's what gave us the results for -1 mod p and 2 mod p. So here we go again. So here we're dealing with we want to say something about the residue status of n mod p. That's a little bit of a mouthful, so I'm going for reading it instead. So what you do is you consider all the multiples of n. Well, excuse me, not all the multiples, just half of the multiples of n. And using the coefficients, the things multiplying n, are all the set of residues from 1 up to p minus 1 over 2. So half of the residues modulo p. Okay, the complete set of residues mod p goes 1, 2, 3, all the way to p minus 1. We're only going to as far as p minus 1 over 2. So again, the first half, remember p is an odd number, so p minus 1 is even. So the residues 1 to p minus 1 split into 2 halves, and the first half and the second half. So we're taking all the multiples of n. And what the theorem says, if you examine these and look at their standard representatives, so when it says the number of residues, it means their standard representatives from the standard set of representatives 1 to p minus 1. So, typically these numbers might be a lot bigger than p, right? But you reduce the mod p. And for each one of them, you have a representative, which comes from the standard set, 1 to p minus 1. What we do is we count the number of those that fall in the second half of the residues. Okay? Remember all the residues, you've got 1, 2, yada, 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 to p minus 1 over 2. That's the first half of residues. Then you've got p plus 1 over 2, yada, 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 to p minus 1. Okay, so that's all the residues mod p. But they split into 2 halves. There's a first half and a second half. Okay. P over 2 is the midpoint, but that's not an integer. So p minus 1 over 2 and p plus 1 over 2 are the ones either side of the midpoint. So you look at all these multiples, you reduce the mod p, get their standard representatives, and the number of them that fall in here in the second half, you just count that number, and that's this count m. M is the count of that. And the theorem says quite simply that the Legendre symbol n mod p is minus 1 to the n. So in other words, it's plus 1 if m is even, of course, and minus 1 if m is odd. So if m is even, this number is a quadratic residue, modulo p. If m is odd, then it's not a quadratic residue, modulo p. That's kind of interesting. It doesn't immediately magically enable you to suddenly evaluate Legendre symbols any particular more easily than we could before, because you can't just magically instantly arrive at this number n. You still have to do a lot of calculations and a lot of checking and so on. Okay? But it's an interesting insight. It's saying something about what's going on, and it's very interesting that the first half and the second half have these consequences. Now, the idea in the proof you'll see is very reminiscent of what we did before in the two cases. Okay? So first of all, we just take all these multiples of n and we multiply them all together. Okay? And just a straightforward, not using modular arithmetic, just straightforward integer arithmetic, if you multiply all together all these multiples, you can factorize n out of each one, and you've got n to the power of p minus 1 over 2. And then the remaining things multiplied together is 1 times 2 times 3 times 4 times times p minus 1 over 2. So that's p minus 1 over 2 factorial. Agreed? Multiple of all the numbers from p minus 1 over 2 down to 1, multiplied by all these n's, and there's p minus 1 over 2 n's. Okay? So that's our first observation. The second observation comes back to these multiples. Oh yeah, and just interestingly in here, n to the power of p minus 1 over 2 is exactly the thing that occurs in Euler's criterion. So this is congruent to the Legendre symbol NP that we're trying to prove something about. So that's good. So now what we're going to do is we're going to again look at the product of all these elements, but not using their actual integer values, instead using what they're congruent to, instead using their representatives. Okay, so each of these is congruent to one of these, yeah? So each of these numbers, you reduce the mod p, you get something in here, right? Now some of them are going to fall in the first half, some of them are going to fall in the second half. There's n of them fall in the second half. Well, for those ones, rather than using this number over here from the second half, we're going to represent it as negative of one of these, right? So everything over here is the negative of its partner over here. P minus 1 is the negative of 1 in modular arithmetic. P minus 2 is the negative of 2. P plus 1 over 2 is the negative of p minus 1 over 2. Okay? So we're going to take all these numbers, replace them with their representatives mod p, but the ones that are here, we're going to represent those as the negative of one of these first half ones. Okay? Now this goes, yeah. That's what this lays out here. So it says if you consider one of these multiples Jn, so we have R being the residue representative of Jn. If Jn does exceed 2, if Jn exceeds P over 2, then it's somewhere in this range. And we can say it's the negative of an S, where S is in the first half, 1 to P minus 1 over 2. So in this way, we associate each multiple Jn an element. So we associate each multiple Jn a signed element of the first half of residue. So this epsilon j is just embodying or recording the plus or minus sign that we use. Okay. Again, all of these, we replace them with their representative from this standard set, except the ones that would be replaced by something here, instead we replace it by the negative of its partner here. So this set of integers is congruent to this set, where you've got now the complete set 1 up to p minus 1 over 2. You've got the complete set of residues from the first half, and they each carry a positive or negative sign, which is represented by the epsilons. There's probably a little detail left out, which you can prove fairly easily, is proving that none of these ones are congruent to the negative of each other. So that when you do this process, taking these, that is p minus 1 over 2 quantities here, when you do this process, what you'll get is each and every one of the p minus 1 over 2 representatives here from this early each carrying either a plus sign or a minus sign according to this specification. Okay. So when you multiply all these together, well, what we can say now is if you go back to our original product, so this is multiplying together n by 2n by 3n all the way to p minus 1 over 2n. When you multiply all those two together, it's equal to this. This is the factorization we just did at the very beginning. But when we pass through now a congruence mod p, we can say this is congruent to this product here. Each of these has been replaced by j, the representative from the first half, and it carries a plus or minus sign, epsilon. But now this, what you're looking at here now, is again the product of all the j's between 1 and p minus 1 over 2. So that's exactly our old friend, p minus 1 over 2 factorial. Again. And then you got a load of plus and minus signs multiplied together. Now, how do you evaluate a product of a load of plus and minus signs? Well, you just ignore all the pluses, and you just have to count carefully all the minus signs. And depending on whether that is odd or even, it'll be plus and minus 1. So multiplying together all the plus and minus signs is just minus 1 to the power n. Remember, m is the count of the number of negative signs that occur here. This is the generalization of the idea from the two previous applications of order structure. Now we've established this congruence here. It's modulo p, and there's this common factor on both sides, p minus 1 over 2 factorial, which the observation we made before is that that is coprime to p, so it's got an inverse, so we can cancel it between both sides. So you do that, and you're left with n to the power of p minus 1 over 2, which is congruent to the Legendre symbol. This must be, well, first of all, congruent to minus 1 to the power n. But if it's congruent to minus 1 to the power n, it must be equal to that, because they're both of them either plus 1 or minus 1. So it's not that one of them is going to be like separated by a load of multiples of p from the other one, congruent in that sense. They actually have to be equal, because they're both either plus or minus 1. And this establishes up here that they're congruent, that this power of n from Euler's criterion is congruent to minus 1 to the power n. So that tells us that the Legendre symbol, which is congruent to that power of n, must be congruent to minus 1 to the m, but when you think about it, it must be equal to it, because they're both either plus or minus 1. So that proves that point. Okay. Now, it doesn't suddenly magically make the calculation of the Legendre symbol easier. It just presents it in a new light, an interesting light. Okay? That it really comes down to where these multiples of n land. Some of them, when you look at their standard representatives, modulo p, some of them are going to land in the first half, and some of them land in the second half. And it's the number of them that land in the second half, or more specifically, it's the parity of the number of them that land in the second half, whether it's an odd number or an even number. But that is indicating whether or not n is a quadratic residue or not, modulo. So that's quite an interesting thing to see. So now our interest is focused on this value of n. Okay? And the question of, NP equals what, as this question now becomes, is m even or odd? So if you know if m is even, then you know this power is plus 1. If m is odd, you know it's minus 1. So this general question, which we presented like in a very introductory lecture on this, how do you determine whether a given n is a quadratic residue or not, modulo something else, modulo p? Now, this is the way we're thinking of the question. Is this number m even or odd? Well, theorem 8.8 gives us insights into that. And it looks rather complicated, but just step back a bit, ignore the mush in the middle, and just look what it is. It's a formula for m modulo 2. Remember, even or odd is the same as, here. Remember, even numbers are congruent to 0 mod 2. Odd numbers are congruent to 1 mod 2. So even odd is the same question as what you are modulo 2. So theorem 8.8, we've got an equation for the congruence class of m modulo 2. So that's going to tell us whether or not n is even or odd. Now, there's a bit of a mouthful here in the middle. It's a summation oh yeah, I need to go back to this notation here. It's a summation here of certain quantities depending on n and p, and some kind of formula involving n and p. But it simplifies somewhat when you're looking in the special case where n is odd. In the special case where the number n is odd, where it will be when we're looking at quadratic reciprocity, because quadratic reciprocity we're looking at one prime modulo another. So the n, the first position in the Legendre symbol, will be odd. So that means this number here, if n is odd, this number here is 0 mod 2. This number is even. So in fact, that thing isn't there when n is odd. And the formula simplifies somewhat. It's kind of an interesting summation formula, again, over the first half of residue classes of this object here. Now, what's this object here? Well, it's something in square brackets. The square brackets actually carry a precise meaning here. These square brackets notation are used for what's called the integer part, or it's also sometimes called the floor. So you have your number line, you've got integers on your number line. In general, you could have a non-integer number x. I can't see that. In general, you could have a non-integer number x. So the dots here, the points in the number line are the integers. In general, you've got a non-integer number x. Well, this number here is the floor of x. It's the biggest integer less than x. Assuming you've got positive on that side, negative on that side, of course. So this integer is called the floor of x. And this distance here between the two, between the floor of x and x, this is called the fractional part of x. So basically, you're expressing any number on the number line as the biggest integer less than it plus a little bit. Yeah, this is less than 1. Really, I guess the floor notation means you turn this whole picture vertically. So the floors are at the integer levels. But your general position here, you're saying, well, it's equal to the floor of x, and the floor of x is this height here on the floor, plus the integer part, plus the fractional part, which is the distance from the floor up to the actual position. And that'll be less than 1. So the distance from the floor to the ceiling is 1. So both at consecutive integer levels. Okay? Indeed, sometimes this number here is referred to as the ceiling of x. So some books will actually use this notation for the floor of x and this notation for the ceiling of x. But in this context, we don't need to refer to both of them. We just need to refer to the floor. So we just use the regular square brackets. So okay, is everybody clear on that? Now it's a simple enough idea, right? Expressing a general number on the number line as the biggest integer less than it plus a little bit. Yeah. So it's a pretty simple idea, but we really go to town with it in the proof of this theorem. Okay, so you have to kind of hold on to your hat somewhat for this. So now we can understand what the result is saying. The result is looking at all these fractions. So this is for evaluating the Legendre symbol of n mod p. Remember, the previous result said n mod p is equal to -1 to the m. And this result is telling us about the m. What the m is modulo 2. So what we do is we look at all these fractions, j times n over p, for every coefficient j from 1 to p minus 1 over 2. These are going to be rational numbers. Okay? These are going to be rational numbers. They're never going to be divisible by p. They're never going to resolve to actual integers, of course, because p is a prime number. So you can never manufacture a multiple of p using numbers less than p. Yeah. So these are all genuine fractions. So we're looking at their integer parts, their floors. And we're adding all those up. And then in general, there's this kind of term here, but in the special case where n is an odd number, well then this n minus 1 is even, and we're talking modulo 2, so that disappears because it's 0 mod 2, and you just have this much more compact formula. And this one is going to allow us, this one is going to give us the proof of quadratic reciprocity. Okay, but this is the last kind of lemma before the proof of quadratic reciprocity. Now, as you'll see on the next page, we really go to town on getting the maximum use of this notation. Okay? So once again, like in the previous result, all our focus is on this set of multiples of n. Okay? So you're looking at all the multiples j times n for every choice of coefficient j from the first half of the standard representatives. Okay? And we apply this idea of this floor and fractional part notation to them, to their fractions over p. So you've got j times n over p. It consists of its floor plus its fractional part. Now, if you turn this, so this is a messy fraction. It's not an integer. But if you multiply across by p, at least then this becomes an integer on the left-hand side. In fact, every bit will be an integer. What we notice here is this is exactly the integer division. This is the integer division with remainder of Jn by p. Okay, so remember all those way back before Christmas when we were looking at divisibility, we were looking at the Euclidean algorithm. We were doing this thing of dividing a big integer by a smaller one. It goes into it a certain integer number of times. Remember, this floor is an integer plus a remainder. Well, when you examine what's going on here, this is exactly what we're looking at here on the right-hand side. Okay. So this last equation does indeed show the integer division of Tn. That's a slight misprint there, not Tn, Jn. Integer division of Jn by p, where the remainder is given by, so Rj, the remainder associated to j, is given by this expression. Now remember, in general, x is the floor of x plus the fractional part of x. So this fractional part, I mean, we want to talk in terms of integers all the time. So we'll turn this fractional part explicitly into an integer. Oh no, sorry. This goes back to the previous equation here. So you've got p times the fractional part is the remainder. So the remainder you can express as Jn minus p times this floor. Just move p times this floor over to the other side, and you get this. So that's from 8.66, the previous equation of the previous equation. Replacing p times the fractional part with Jn minus p times the floor. Now, remember back to Gauss's lemma, Gauss's theorem. We looked at all these multiples. We looked at the multiples Jn. We looked at the standard, we looked at their representatives. So these are the reps mod p of all the Jn's. Representatives mod p of all the Jn's, where j comes from 1 to p minus 1 to 2. These were congruent to this set here. You've got each of the congruence classes from the first half, 1 to p minus 1 over 2, but they're all signed. They each carry a plus or minus sign. Right, and then we just go, then we analyze this. Now, okay, I mean, I'm not going to lie, this is to discover this proof again and to kind of make your way and see why all these choices and actions are being done is a little bit tricky. There's quite a lot of results piling up here. But the thing that we're trying to get at is this number n. Okay? So what's driving this sequence of summation equations we're going to go into now is generating an evaluatable kind of equation, a good equation that features the n, and that we can reduce it mod 2 to this required form. And in the special case of where n is odd, which it is going to be when we're considering quadratic reciprocity, so you got one prime modulo another, it's going to simplify somewhat to this nice expression, which has a very interesting, this expression has a very interesting geometric interpretation. That the proof of quadratic reciprocity that we include in this course is quite a geometric one. And this summation of floor values has a very strong and simple enough geometric meaning. So that's what we're going for here when we launch into this sequence of equations. We're going to generate something that m is going to feature here and pop out. And we're then going to isolate m, or make m the subject of all of this whole thing. So the way we get there is we add up all these representatives of all the multiples of Jn. So that means so first of all, we're representing them as plus or minus these representatives from the first half. So we're not yet passing into congruence mod p here, but we can split this set up into two. There's the j's that carry the plus sign over here. So those are exactly equal to, if the ones that carry the plus sign, they're present over here and they're also present over here. The ones that carry the minus sign, so where epsilon j is equal to -1, so there's a residue over here, but it's represented as minus something from the first half over here. So to get back to its proper value, you have to consider p minus j to return it back into the second half of residues that it is actually equal to here. Okay. So this is summing some of the j's between 1 and p minus 1 over 2, those that carry the plus sign here. And this one is summing their negatives, p minus j, which gets you back into the second half. And we do that when the j occurs here with the negative sign. So it's quite detailed and picky, but it separates out the sum of all these integers according to whether they carry the plus sign or a minus sign. When you looked at the multiple j times n, and you reduce it. Right. On the left-hand side here, we replace our j with this representative here, jn minus p root jn over p. Okay, so this is the remainder after division by this thing, so you can replace it by this. On the right-hand side here, you leave this sum alone, that just occurs there. Now this sum here, well, j is a changing parameter. J goes through certain values, but p is just a repeated constant here. So we can separate out all these p's and bring them out here to the front of the sum. So you're left here with the minus the sum of all these certain j's that satisfy this, and there's some amount of p's. How many p's are there? Well, it's the number of terms in this whole sum. And this whole sum only goes over the j's with epsilon j negative. So we've got a name for the number of those. M is the count of the number of j's for which epsilon j is negative. That's from the statement. So check the definition of M from Gauss's result. Okay, this M is exactly the count of the number of multiples Jn which land in the second half. And those are all the ones that picked up this minus sign. So that's where the M enters into the discussion. Then in the next line, we leave the right-hand side all alone, and we work on this left-hand side. Well, it's a sum of these differences, so we just take the sum of the first bits minus the sum of the second bits. Break it apart. Again, these n are, no, what's fixed here? Yeah, the n is fixed for every term j in the sum, so you can factorize it out. You factorize out the n. Now you're looking at the sum of all the j's from 1 to p minus 1 over 2, with no extra qualification, just the sum of all the j's. Just make this a little clearer by, you could put brackets around here. I mean, the presence of the brackets is implied, but just to emphasize it. And then you got the sum of all minus the sum of all these, but again, p is a fixed quantity, so it can factorize that. Now you see, this is the thing that's mentioned in the result, and here's our m over here. So we're getting close to the result. But now eventually we're going to reduce this whole equation modulo 2, but we do a neat kind of trick before we do that. So because at the moment we're dealing with these two separated sums here. And there's m terms j in this sum, and p minus 1 minus m terms in this sum here. Well, we do a kind of clever manipulation here, and it involves this sum here. So when you look at the sum of all the j's, that's just equal to the sum of these two. Okay. This is just saying the sum of all the j's is the sum of all the j's which carried a minus sign plus the sum of all the j's which carried a negative sign. Because remember, in this set of all the residues from 1 to p minus 1 over 2, we had this classification of them. Some of them were associated to a plus sign, some of them were associated to a minus sign. So if you add them all up, you're adding up all the ones that had a plus sign and all the ones that had a negative sign. And you take this, and what do we do with it? We add this onto both sides. So you got this quantity, you add it to the left-hand side, add it to the right-hand side. The benefit of adding it to the right-hand side, of course, is these two are going to cancel with each other. There's a negative sign and there's a plus sign. So those two are going to negative with each other. This one here, you're adding onto this, which gives us 2 times all of that. So we add this right-hand side to the right-hand side here, and to the left-hand side, we choose to add the left-hand side. It's fine, because they're both equal. So this thing you add onto here, so that bumps this up, that's going to bump that up to n plus 1 times this. Because you're just adding on this. This is the bracket there. So we haven't gone modular yet. We're still working with an equation, but we've simplified the right-hand side somewhat. But more interestingly, we've introduced a factor of 2, which is going to disappear, of course. This whole 2 times this is going to be nothing when you take this whole equation modulo 2. That's what we're doing now. So this thing, as complicated as this looks, it's going to simplify quite a bit when you look at it modulo 2. When you look at it modulo 2, so this is your mod 2 glasses looking at this equation. It's printed properly on the next page, but just look at what happens. When you look at this modulo 2, this whole thing goes, because it's got a factor of 2. The p goes, because p is congruent to 1 mod 2. So this just will reduce to an n. This p goes, because that's just 1 mod 2. And that's n plus 1 there. This is adding up all the j's. Well, we can just use the arithmetic sum formula for adding up all the j's. You'll get some kind of expression involving this. That's the p squared minus 1 over 8. It comes. This is the thing that's in the statement of our result. That's going to go, and there's the n. So you can see the result just pops out now. And you consider that equation modulo 2. So we consider it modulo 2. We get this equation here. And yeah, we just do a slight shuffle of the feet and say that, well, n plus 1 is congruent to n minus 1 mod 2. To be honest, you could have stated the original theorem with an n plus 1 here, but for some reason it was stated with an n minus 1. But the point is, it's a mod 2 formula, so the two things are equal modulo 2. So it's neither here nor there. That p squared minus 1 over 8, that's just your arithmetic sum formula for the sum of j's from every j from 1 to p minus 1 over 2. Apply the sum formula there. Remember, it's p plus 1 over 2. It's the top limit plus 1 times half the top limit, so p minus 1 over 4. So that gets you your p squared minus 1 over 8. And that's our result. And when n is an odd number itself, this n minus 1 is even, so that whole thing is going to be 0 mod 2, and then we'll be left with the simplified form. Now, all of that is quite a mouthful to take in. It's quite technical, careful work with the summation formula. But this interesting result is going to gives us a proof. We'll see next time a proof of the quadratic reciprocity law using its geometric meaning. So this expression, adding up all these floor values, actually means something quite clear and systematic when you look at it in a geometric sense. And that's going to give us that. Okay, so I'll see you tomorrow for tutorials tomorrow, I believe. Yes, it's big date. And I think we'll mainly be looking at our factorized flip reduce algorithm using quadratic reciprocity and maybe some associated things. Okay then, thanks for your attention. I shall see you later on.